Once again, welcome to my YouTube channel. In the previous video, we learned about relative velocity method. Now in this video, we understand the acceleration analysis along with examples. Please see this video till end to understand the concept completely. I am sure that after seeing this video, there is no doubt in acceleration analysis. Now we have considered a rigid link. This is a rigid link, and there are 2 points, point A and point B on the rigid link. So we want to find out the acceleration of this B point with respect to point A. So this link is rotate with an angular speed of omega into the anticlockwise direction with respect to point A, and it is having an angular acceleration alpha. Alpha is nothing but the rate of change of omega. And if we see the acceleration of this point B point with respect to point A, there are two components. One is towards the line joining B to A, or towards the center of rotation, means about point A, and that we are calling as a radial acceleration, that is ARBA, and this is nothing but the centripetal acceleration. So A means the acceleration and R means the radial component of the acceleration, and BA means the point, the acceleration of point B with respect to point A. And this is along the line joining B to A, means towards the center of rotation. We have the other component that we are calling as a tangential component, that we are calling as a ATBA. Acceleration T means tangential of this point B with respect to point A. And this is nothing, this is parallel to the velocity component VBA, means the relative velocity of point B with respect to point A, or it is perpendicular to the line joining B to A. So this is the space diagram basically. Now if we have to draw the acceleration polygon, this is the acceleration polygon from this diagram. So if we see so there are two components of the acceleration. One is called the radial component of acceleration, that is towards the center of rotation, and other is called the tangential component, which is perpendicular to the line joining these 2 points. And the net value of the acceleration of this B point with respect to point A is nothing but the vector addition of these two accelerations. So again, because we are finding out about this A point, so we mark A dash as a pole point, and from this A dash point we draw a vector from B to A, means these are in the down direction, this is from B to A, whose value should be equal to the radial acceleration ARBA. So this is the point A dash. So we draw a vector which is representing the ARBA. So this A dash x vector is representing the radial component of the acceleration, and this acceleration is parallel to the line joining B to A. Now this tangential, we know this is perpendicular to the line joining B to A, so we draw a vector x B dash which is perpendicular to this line joining B to A, or it is parallel to the velocity component basically, or it is perpendicular to this A dash x component. So this is representing the tangential component of acceleration on point B with respect to point A. So we are getting point B dash. We join this A dash to B dash, so we are getting the net value of the acceleration of this B point with respect to point A. Here you see that in the velocity polygon we have used the small alphabets, and here we are using the dash symbols of the small alphabet, means A dash, B dash as such, to representing the acceleration, okay, of the 2 points. Now this radial component of acceleration, as already we have discussed, this is the centripetal acceleration, and this is nothing but the V square VA divided by AB, means the velocity of this B point with respect to point A, the squaring of that velocity divided by AB, means we know that the centripetal acceleration is nothing but the V square by R basically. So from that formula we have to find out V square by R, or R omega square, is the same thing. So we have to, with this formula we have to find the value of the radial component, and we know its value numerically basically. Velocity we are getting from the velocity polygon. The tangential component of acceleration that we are calling as the ATBA, this is nothing but alpha into AB. Alpha is the angular acceleration and AB is the length of the link, where alpha is nothing but d omega by dt. So this way we have to find out the tangential component of acceleration, and we draw these two accelerations with substitute with the scale, okay, and then we can find out the final acceleration of this B point with respect to point A, that is A simple B. If suppose for some of the link, if omega is constant, it is not changing with respect to time, then alpha value is 0 in that case. And when alpha is 0, so ATBA is 0 value. This component is means XB dash is 0 in that case. And the net value of the acceleration, so here we are getting only A dash point, and directly we are getting the B dash point basically. And this radial component of acceleration is representing the total acceleration, means ABA of this B point with respect to point A. Again, we have considered a rigid link, and we have taken 3 points on the link: point A, point B, and point C. This link is rotates into the anticlockwise direction with an angular speed of omega. So we have the location of this C point. There are 3 points A, B and C. So the location of this C point is, it is making an angle theta with respect to point A. It is making an angle phi with respect to point B. So this way we can locate this C point. The relative velocity of this B point with respect to point A is known to us, that is VBA, and that is perpendicular to the line joining B to A. Okay. The absolute acceleration of this A point, this is in this direction. So this AA is known to us in magnitude and direction both. This AB, the absolute acceleration of this B point, this is known to us only in direction but not in magnitude. So this is a space diagram, and from this space diagram let us see how to draw the acceleration diagram and how to find out the different radial and tangential components and the acceleration of this C point with respect to some other point. So first of all we mark a pole point, that is O dash. First of all, this A is known to us in magnitude and direction. So with some suitable scale we can draw a line which is parallel to this AA and we can reach to the point A dash. So this O dash and A dash is known to us in magnitude and direction. So easily we can locate this A dash point. Now we have to locate this B point. Now as we know that this AB is known to us in direction only, not in magnitude. So from this O dash point we draw a line which is parallel to this AB vector. So this is that line. We do not know where it is cutting the other line basically, so we can extend this. But we know the acceleration of B with respect to point A. It is having two components. One is the radial component, that is towards A, or it is from B to A, and it is having some tangential component which is perpendicular to line joining BA or in the direction of VBA. It is parallel to VBA or perpendicular to the point joining B to A basically. So two components we have, radial and tangential. So from this A dash point we draw a line which is parallel to BA, and it is direction is from B to A into the downward direction. So from A dash we draw a line A dash x which is representing the radial component of acceleration of point B with respect to point A. The tangential component again is perpendicular to BA, or it is perpendicular to A dash x. So from this A dash x we draw a line which is perpendicular to A dash x or BA or parallel to VBA. So this is that line. So this angle is 90 degree here. So with this x point we draw a line, and these two lines, the tangential component of acceleration of B with respect to A and the absolute acceleration of B, where these two lines are meeting, we are getting a point B dash there. We join B dash with A dash, so we are getting the net value of the acceleration AB, acceleration of B with respect to point A, and it is nothing but the vector sum of the radial component A dash x and the tangential component x B dash. So this way we are getting the acceleration of B with respect to A. Now to locate this C point, so we see that the location of this C point, it is making an angle theta into the clockwise direction with AB line. So from this A dash B dash line, we draw a line at an angle of theta. This theta is into the clockwise direction. So this is that line. We do not know where it is extending or where it is cutting the other line, so we can extend that line. Now the location of this C point with respect to point B, it is making an angle phi into the clockwise direction with respect to the BA line. So from this B dash A dash at an angle of phi into the anticlockwise direction, we draw the other line. So where these two lines are meeting, there we are getting a point C dash. Okay, so this way we will see that if the angular position of any of the point is given to us, okay, so we can locate this way this C dash point. We join C dash with B dash. This gives the acceleration of C with respect to point B. If we join C dash with A dash, so we are having the acceleration of C with respect to point A, and the direction is from A dash to C dash, and here for ACB direction is from B dash to C dash. This is one of the way when the angles are given. The other way is to locate this C point is we have the acceleration of C with respect to point A having two components. Radial component is from C to A, or it is towards A, and tangential will be perpendicular to this one. So all the radial component of acceleration we know, because we know that radial acceleration is nothing but the v square divided by the length of the link. So v square we are getting from the velocity polygon. So radial component of acceleration we know of all the points with respect to some other point. So here the radial acceleration of C with respect to point A we know, and it is from C to A, means it is into the downward direction basically. So So from A dash, we draw a line which is parallel to CA, and its direction is from C to A, means into the downward direction. So this A dash Y is representing the radial component of this C point with respect to point A. Tangential component is perpendicular to CA. So from this Y at an angle of 90, we draw the other lines. We can extend this. We do not know where it is intersecting the other lines. The acceleration of radial component of acceleration of this C with respect to point B, it is from C to B, or it is towards B, which it is into the upward direction. So from this B dash point, we draw a line which is parallel to CB, and this is from, the direction is from C to B basically. So this is in this direction. So we are reaching to the point Z, because B dash Z or A dash Y, these two lines we know its magnitude basically and direction both. The tangential component of this C with respect to B is perpendicular to the CB. So from this Z point, we draw a line which is perpendicular to CB, and wherever these two lines, means the line extending from Z and the line extending from Y, where these two lines are meeting, there we are getting the point C dash. So this way we can also locate this C dash point. So we see that the C dash point will be located in terms of angular position, or maybe with the radial and tangential component. Now if we measure Z and C dash, so it gives us the tangential component of point C with respect to point B. If we are measuring C dash and Y, so it is giving the tangential component of the C point with respect to point A. So with this tangential component, we can know the angular acceleration of this C point with respect to point A, or with respect to point B as well. So we see that how we are getting the tangential and radial component, and how we have to locate their directions and everything with the help of the acceleration diagram. So here we have taken one example. So in this example, we have this type of mechanism where we have a single slider crank chain from O, A and B, and with the C point we attach one more slider. Okay, that is moving into the vertical direction. So two sliders are attached, one is with B and other is with C. At this instant, when this AO link is making an angle 30 degree with this BO line, at that instant we have to find out all the things. So this omega AO, the angular speed of this A point with respect to point O, is given as 2.1 radian per second, and it is moving into the anticlockwise direction. The length OA is given to us, that is 300, and this AB length is given as 2000 mm. Okay. This BC is given, the location of this C point is given as 450, and this CD, the location of this D point, is given as 450 mm to us. So with this information, with the dimension information and with angle or everything, we can draw this space diagram first of all. So first of all is to draw the space diagram with some suitable scale, and after that, as we discussed that, the first step is to draw the velocity polygon, and then we have to draw the acceleration diagram with the velocity diagram. And we have to find out the following things. Number one, the velocity of this B point. This B is the slider here. So we have to find the velocity of the slider. Then omega CD. This CD is this length. So we have to find out the angular speed of this omega CD. Then we have to find out the AD, means acceleration of this D point. And then we have to find out fifth point is alpha CD, means from the same link CD we have to find out the angular acceleration. So these five things we have to find out. To find out this thing, first of all we draw the velocity polygon. So already in the previous slide we have discussed it, how to draw the velocity polygon. Again we can consider it here. So because we know this VA, we know, because VA is nothing but R into omega. R is the AO and omega is given as 2.1 radian. So we know this magnitude basically. So what we do, we take a pole point here. Suppose this O point we have taken as a pole point, and from that point we draw a vector VA. Okay, and we know this vector in magnitude direction both, so we can easily locate this point A. Okay, from this point A, if you locate this B point, so we draw a line which is perpendicular to this BA. So from this A point, we draw a line perpendicular to this one. We do not know where it is intersecting the other line basically. We know the velocity of this B with respect to point A is always along the BO line. So from this O point, we draw a line horizontal, and where these two lines are intersecting, there we are getting a point B basically. So, and we join B with O, so we are having the velocity of point B. When we join B with A, so we are having the velocity of this B point with respect to point A. Now this location of the C point is given. So on this BA line, we can easily locate this point C. From this C point, we know that the velocity of this D point with respect to point C is perpendicular to the line joining CD. So from this C point, what we are doing, we are drawing a vector which is perpendicular to the CD line. So this is suppose that vector. We do not know where it is intersecting the other vector. Now this, if we see the motion of this letter T, it is always having into the vertical direction. So with respect to point O basically, or the pole point. So with respect to point D O, we can draw a perpendicular vector. Okay, and where these two lines are intersecting, we are getting a point D. We join D with O, we are having the velocity of this D point. If we join C point with O, so we are having the velocity basically of this point C. Okay. So we have to find the value of BB. So we can measure this BO length, and as per suitable scale we can convert it to the velocity vector. So this gives the value of BB to us, then this VD. So this OD vector we measure, and this gives the velocity of the D basically. Similarly, omega CD. Omega CD we have to find. This is C and this is D. So omega CD is nothing but VCD divided by the length of the CD link. Already in the previous video we have discussed how to find out the omega and their direction. So this way we have to find out the value of omega CD basically. So from here this VB value is coming out to be 0.4 meter per second. This D slider having a velocity of 0.2 meter per second. This omega CD already we have discussed that VCD divided by CD we have measured. So this CD length we have to measure, and we put this value here. This is coming out to be 0.82 radian per second. Now to find out the acceleration of this point D here and this alpha CD, we have to draw the acceleration diagram. So this is the acceleration diagram. So let us see how to draw the acceleration diagram. So first of all, because this O is a pole point here, so in the acceleration diagram, as we have seen that we use the dash of the alphabets, small alphabets. So this is O dash here. Now this omega is constant here because there is no information is giving about the alpha for this O link. So we assume only one component, that is the radial component of this. So the acceleration of this A point with respect to point O is always towards line joining from A to O. So from this O dash point, we draw a vector. This is that vector. Okay. We draw a vector O dash to A dash because we know its magnitude. How we know the magnitude? With the radial component of the acceleration, this is V square by length of the link. So VAO, so means the velocity of this A point we know, and divided by the AO length, so we know this radial component. So O dash and A dash we know in magnitude and direction both. This way we can locate the point A dash. From this point A dash we have to locate the point B. So we have to find out the acceleration of point B with respect to point A. So when we are finding out the acceleration of one point with respect to other point, it is having two components, radial and tangential, because it is having omega and alpha both as we assume. So this B, the acceleration of this B point with respect to point A is line joining from B to A. Clear? So from here A dash point we draw a vector A dash x, okay, which is means from B we have to draw a vector from B to A basically, okay, in this direction. So from here A dash we draw a vector A dash x which is parallel to BA line. So this is that vector A dash x. This is again the radial component. So radial component of this vector we know because we know the velocity of B with respect to A. So this is, suppose this is point B here and this is point A. This velocity vector we know, and we know the length of the BLE. So this A dash x vector we know basically. So easily we can locate this point x. Now the tangential component of the acceleration of this B point with respect to point A is perpendicular to A dash x. So from A dash x we draw a perpendicular line. We do not know where it is intersecting the other lines. Let me see where it is intersecting. So we draw a perpendicular line basically. Okay, from this A dash x vector. Now if we see the acceleration of this B point with respect to point A, because this B point is always having a motion along, because the velocity vector is along BU. So similarly the acceleration vector is also along BU. So from this O dash point we draw a vector which is parallel to BO, and from O dash vector we draw this vector. So this line, okay, this O dash B and this X B dash, they are meeting at point B dash. So this way we are getting the B point basically, or the acceleration of this B point. We join B dash with A. So this is the acceleration of B with respect to point A. We join this O dash with B. So this is the absolute acceleration we can call. This is we are giving a value A in this case here. Now after that we have to move to the point C. So we know the location of this point C here because all the distances are given BC and AC, and this way we can easily locate this point C. So same, this C point is on the line B. So B dash A dash is the final acceleration. So on the same line we can mark this point C or C dash basically. The C dash point we can locate easily on this acceleration, final acceleration line also. Okay, because we know the distances. So in the ratio in which is divided this C point divided the space diagram or this BA line in the same ratio, this C dash divided this B dash A dash line. So this way we can locate the C dash point. We join O dash with C dash, we give the acceleration of this C point basically. Now from C point we have to move to the D point. So acceleration of this D point with respect to point C having two components, radial and tangential. A radial component is always from D to C. Okay. So from this C point we draw a vector which is parallel to DC basically. So this is in the up direction. So from C dash we draw a line that is CY, which is parallel to DC, and this line is joining from D to C basically means in the up direction. We know the magnitude because this is a radial component, so all the radial component of the acceleration we know because we know the value of this CD and we know the length, so we do V and CD square divided by CD. So this way we got this value CD square. So Y point is easily we can locate. Now it is having some other component of acceleration also that we are calling as a tangential one, which is perpendicular to the line joining CD. So from this Y point we draw a line perpendicular to C dash Y, and that is representing the tangential. We do not know where intersecting the other lines basically. Now if we see the acceleration of this D point with respect to point O, it is so this because it is the velocity of this D slider is always in the vertical direction. So similarly it is having acceleration into the vertical direction. So from this O dash point we draw a line which is perpendicular, or we can say okay, which is perpendicular to this vector. So from this point O dash we draw a line O dash D dash. So this line and this tangential line or this CD link where they are meeting at point D dash. So this way we are getting the point D dash. We join D dash with O, we got the acceleration of this D point. Okay. And if we join this D dash with C, we got the acceleration of this D point with respect to point C. So this way we can complete the acceleration diagram. And now we have to find out the AD. So we can measure this AD vector here, and as the suitable scale as whatever we have assumed. So we got the acceleration of this AD point. So this AD acceleration is coming out to be 0.16 meter per second square. If we are finding out the acceleration, okay, the angular acceleration of this CD link, this is the CD link basically. So we know that the tangential acceleration of CD link is ATCD is nothing but the alpha CD multiplied by the length of the CD. So alpha CD is nothing but the tangential component of acceleration divided by the length of the CD link. So the tangential we have now once we complete this acceleration diagram, so the d dash y vector we have measured. This vector will give the value of the tangential acceleration. So this value we have to put in 1.28, and the length of this CD link we have to put it here, that is 0.45, because this CD length is given as 450 mm, it is 0.45 meter. So this way once we divide it, and so we are getting a final value, okay, of this acceleration. So this way we have to find out the acceleration. So velocity and omega we got from the velocity diagram, and the acceleration and angular acceleration we are getting from the acceleration diagram. So we have considered the second problem. In this diagram it is shown as a toggle mechanism. All the dimensions are given to us here. This OA is 180, CB is 240, AB is 360, BD is 540 mm, and then OC is 360 mm. So all the dimensions are given to us. This OA rotates into the anticlockwise direction with an angular speed of 18.85 radian per second, and this speed is increasing at a rate of 50 radian per second square. So this is alpha basically. Now this space diagram we can easily draw with these dimensions. And after the first step is to draw the space diagram, then the second step is to draw the velocity diagram, and third is the acceleration diagram. So as we see in this problem that AO is having both omega and alpha, so it is having two components of acceleration. So first of all let us see how to draw the velocity polygon. So the velocity of this A with respect to point O is given to us. It is perpendicular to AO, and we know its magnitude because we know the value of VA is nothing but R into omega. Omega is for AO link, and multiplied by the length of the link AO. So this all the data is given to us. This O and C are the fixed pin joint here, so we can mark them as a pole point at O comma C. So first of all, we draw the vector VA, which is perpendicular to AO line, and we know this VA in magnitude and direction both. So from this O point, we draw a vector VA, or we draw a line VA, and we can locate point A. So this A to O, this is given us. This gives us the value of VA. Now the velocity of this B point, after reaching to A, we have to reach to the point B. So the velocity of this B point with respect to point A is perpendicular to the link joining BA. So from this A point, we draw a line perpendicular to BA. We don't know where it is intersecting the other lines. This B point is also attached with C point. So the velocity of this B point with respect to this C point is also perpendicular to the line CB or link CB basically. So perpendicular to that link, we draw a line from this C point, and this is that line where these two lines are meeting. We are getting a point B there. So this is, we join B with the C, so we are getting BBC. We join B with A, we are getting B. After B, we have to locate this point D. So the velocity of this D point with respect to point B is perpendicular to the BD. So from this B point, we draw a line perpendicular to BD. We do not know where it is intersecting the other lines, but we know that it is a slider. The slider is always moving as per the given configuration along CD. So we draw from this C point, we draw a line which is parallel to CD, and where these two lines are meeting, the line is coming from B and coming from C, these two lines are meeting at point D. So there we are getting point D. We join D with B, so we are getting VDB, velocity of D with respect to B, and if we join D with C, so we are getting the absolute velocity of the slider. So this is our first step to find out the VD. So VD, we can measure this vector VD, and this value is coming out to be 2.05 meter per second. Then this omega BD, omega, this is B and this is D. So VDB we know, and if we divide VDB by length BD or length DB, though we got the value of omega BD. So omega BD is coming out to be 4.5 radian per second in this problem. The other data, we have to find out the acceleration and the angular acceleration. So we have to draw the acceleration diagram for this. This is the next step. So again, because O and C are the pole points, so we have marked O dash and C dash into the velocity, into the acceleration polygon, O dash and C dash. So with respect to these O dash and C dash point, so as we know that, first of all, we start with A point. So we know the radial component of acceleration and tangential. A radial component of acceleration of this point O, A with respect to point O is towards O, means it is from A to O into the downward direction. So first of all, with this O dash point, we draw a vector O dash x. This vector is O dash x, and this gives the radial component of this acceleration of O, A with respect to O, and this we know in magnitude and direction both. Tangential component will be perpendicular to O, AO, or perpendicular to O dash x. So, and this also we know because we know the value of alpha and the length of the link AO. So tangential component is nothing but it is alpha into length of the link. So x, we draw a line which is perpendicular to O dash x, and this is that line. So we are reaching to the point A dash. We join A dash with O, so this gives the absolute acceleration of A with respect to point O, or this is AA. After reaching to the point A, then we reach to the point B. So the acceleration of B with respect to A having two components, radial and tangential. Radial will be from B to A and tangential will be perpendicular to BA. So from this A dash point, we draw a line A dash Y, which is representing the radial component of B with respect to A. And this A dash Y we know in magnitude and direction both, because radial component of acceleration of all the points with respect to some other point we know basically. So we can locate point B. Tangential component of B with respect to A is perpendicular to B. So from this Y point, we draw a line perpendicular to this A dash Y, and this is that line. We do not know where it is intersecting the other or the point. This B point is also attached with C point. So the velocity of this B point with respect to this point C having two components, radial and tangential. Radial will be towards C, it is from B to C, and tangential will be perpendicular to this link basically. So from this C dash point, we draw a line which is parallel to BC, that is towards C into the downward direction. So from C dash point we draw a line C dash Z. So this C dash Z will represent the radial component of B with respect to point C. Tangential will be perpendicular to B, C. So from Z we draw a perpendicular line, and where the line extending from Z and the line extending from Y, they are meeting, there we are getting point B dash. So we join B dash with C dash. So we have the acceleration of B with respect to point C. After reaching to the point B, now we have to reach to the point B. So the acceleration of this D point with respect to point B having two components, radial and tangential. A radial component of acceleration of this D point with respect to point B is into the upward direction, basically means from D to B. Okay, this is the acceleration of D with respect to point B. So already we have reached to the point B, now we have to reach to the point D basically. So we have draw this B dash S vector that is representing the radial component of D with respect to B. This is from B dash to S. And tangential component will be perpendicular to BD. So from this S point we draw a perpendicular line. We do not know where this line is intersecting the other lines, but we know that because D is having a slider, it is also having a velocity along CD, and it is having an acceleration also along CD. So from this C dash point we draw a horizontal line, the line along CD, and that line where these two lines are meeting, the line extending from S and the line coming from CD. So there we are getting point D dash. So we join D dash and B dash. So this D dash and B dash line will representing the acceleration of D with respect to point B. If we join D dash with any of the pole points, so we are getting the absolute acceleration of point D. So this way we see that how to complete this acceleration diagram and how to find out the acceleration of the other links. Next we have to find out the AD. So from here, from the acceleration diagram, this D dash and this vector O dash and D dash we measure, and this give the value of AD to us. Now we have to find out the alpha BD. So this AD is coming out to be 13.3 meter per second square. This alpha BD is nothing but alpha we are getting from tangential component. So this is, we know that tangential component of this DB link divided by the DB link. So this is D and this is B, and this D dash and S is the tangential component of point D with respect to point B basically. So as D dash S we measure here, so this is the value of ADDB, and we divide this dB, this is coming out to be 71.3 radian per second square, and this is into the clockwise direction because we know the direction of omega into the same direction we have the direction of alpha basically. So this way we see that how with the velocity polygon we have completed, how we draw the acceleration diagram, and how to find out the angular acceleration and acceleration of any of the points on any of the linkages. Thanks for watching this video on acceleration analysis of mechanism. We see that how to draw the acceleration polygon and how to find out the different parameters like acceleration of any of the points or sliders or angular acceleration of any of the link with the help of the acceleration polygon. In the acceleration polygon we have two component of acceleration, radial and tangential. We see that how to find out the directions. Okay, so very precisely and very accurately we have to mark the direction, otherwise we are getting some wrong answer and we are drawing the acceleration polygon into the wrong way. Thanks for watching this video. Please like, subscribe and share this video.